This is a help video for the Laplace Analysis Game in Circuit Tutor, Level 2, Problem Type 1. So we're in that game menu now. And of course, you should have already watched or done the introductory tutorial associated with the Laplace impedance simplification game, which will provide all the basic information you need to understand and work this type of problem. So we're assuming you've done that, and then also it's a great example to look at some examples to begin with here before you start working the problems. Now, for the interest of time, I'm going to just jump straight into a problem. It has to think a while doing some computations. Okay, so here is a problem, and we see that this is going to be a second order circuit with a capacitor and an inductor, and a couple of resistors, as well as a step function source. So our first task is going to be to convert this from the time domain, where we have the farads and the henries and the time, into the Laplace domain, where we have only ohms and S values, no time at all. So in order to do that, to begin with, the resistors stay the same, so we don't have to do anything with them. For the capacitor, remember that the impedance of a capacitor is 1 over SC, so that's going to be 1 over, in this case, the quantity 2S, since we have a very large 2 farad capacitor. For the voltage source, since that's a step function 2u of t, the Laplace transform of that would just be 2 over S. And again, if you didn't remember that, that can be obtained from the Laplace transform table. It's always available here. And then finally, for the inductor, we have an 8 Henry inductor, so that becomes SL, or just 8S, in the Laplace domain for its impedance. And then our sought variable, which was V0 of t in the time domain, has been converted into V0 var, or the bold version here, in the Laplace domain by the program. So we're done with that. Now we'll check that, and that is correct. Okay, so now it's going to redraw the circuit for us again in the Laplace domain, and it's advising us that in this problem we want to simplify things using the circuit editor before we start to do the analysis, because that'll make it easier to analyze. Again, you wouldn't want to do nodal or mesh analysis or anything like that if you don't have to. And by simplifying the circuit, it's pretty clear we have two elements in parallel. That will change it into a single loop circuit, which is simply a voltage divider. And that would be a much better approach than doing one of the brute force methods. So we're going to click the button to go into the circuit editor. And now, again, as I said, we're going to combine these two elements in series. And so, done that here on paper. So two elements in parallel, I misspoke. And because they're in parallel, connected to the same pair of nodes, it's easier to add their admittances to find the equivalent admittance. So the admittance associated with a 1 ohm resistor is a 1 Siemens. And the admittance here is the reciprocal of this value, so that would just be 2S in Siemens. And then combining that is easy. It's just 2S plus 1 Siemens. And then the equivalent impedance is just the reciprocal of that value. So the reciprocal of the admittance, remember it's always denoted with Y, giving us the impedance denoted as Z, is just 1 over the quantity 2S plus 1. So I'm going to just keep this element, and I'm going to enter 1 over the quantity 2S plus 1. Again, I have to use parentheses to make sure everything is in the denominator. And also, because that's now a general impedance, not a capacitor anymore, I do need to change the type of the element to a generic passive element by clicking on that button there. Or I could also have used the drop-down menu for element type to go to a generic impedance. Now, because we're combining the 1 ohm resistor into that, the 1 ohm resistor is no longer going to be there. And in particular, we need to replace it by basically an open circuit, not by a short. If we shorted it, that's saying that everything was shorted to begin with, which is not the case. So to delete that, I can just use the delete key on the keyboard. And then we can check our combination here to make sure we've done that correctly. And it is correct. And then we could perhaps, if you like, do more simplification to add things in series, but it's not totally necessary here because our our terms in Circuit Tutor can accommodate up to 3 elements that are in series, so I won't bother to add these 2 values here. I'll just go and do that, do the algebra on this circuit. Okay, so now we have clearly a voltage divider circuit. And by the way, I will mention this problem was easy because we just had to combine the elements in parallel. Sometimes, for example, if one of those elements had a sought current, you might have to do a sought variable transformation, changing the current into a voltage, for example. And that's possible, as you've probably done before, in the circuit editor as well. We didn't need to do that in this case, however. Okay, so we want to do a single loop or single mesh pair analysis here. And really, we can just use the voltage divider formula, and that's the only way it's going to really let us do it anyway. So we choose sought branch voltage. And so we have our V0 sought variable. That's going to be equal to, this is the standard voltage divider formula when we have 3 impedances. So we need the value of the source. So that's going to be just the 2 over S in the Laplace domain. Again, we're not in the time domain anymore, so we have to use all Laplace variables. And we also need to always check polarity. Remember, if we get polarity wrong, the answer is going to be wrong. So we check that the positive side here is connected to the positive side of the sought voltage, the negative side goes to the negative side. So these 2 polarities are consistent with each other, which means we do need a plus sign. Had this been reversed, or perhaps this been reversed, we would need a minus sign here. It's very important to always check that. Don't just assume it's going to be positive. Okay, then in the numerator we need the impedance of interest. That's going to be the 8S ohms. So we just type 8S there. And then we can also put that down here. And then we have to add in the other 2 impedances. So we'll have, say, the 1. And then we're going to have the combined impedance, the 1 over the quantity 2s plus 1 for the z1 value. And again, you can't just type z1 here, you have to put in the actual value. Okay, so that would be correct, hopefully, and we'll check that. And indeed, it is correct. However, we haven't really solved explicitly because this is still a complicated algebraic expression, so we're going to need to do more. But we have all the equations we need, so I'm going to just click No More Equations. And then it's going to enter a more explicit or simplified value, basically, for this. Now, it also notifies us that because we're going to be doing an inverse transform for this quantity in the next step, that we need to factor any quadratic terms that are going to occur. And we will, in fact, have quadratic terms because, as you see, this was a second-order circuit. And so we're going to have a pair of poles, meaning a quadratic term. So we will have to factor that. Okay, so prepared that on paper here. And so we'll take our basic expression, which is the 2 over s multiplying, and I've just dropped the units here because the answer is going to be in volts, that's fine, and then the ohms all cancel out. So we can get rid of our units here, having checked that they're consistent. And so we have the 2 over s voltage value times the 8s here, and then the denominator, the 8s plus 1 over the quantity 2s plus 1. Now, again, we always want to simplify in algebra as soon as you can. Never miss a chance to simplify because that makes our life easier. So here we have an s in the numerator and in the denominator, and so we can cancel those out. And of course, then we can multiply the 2 by 8 to get 16. Now, we also need to get rid of the fractions inside fractions. So to rationalize this expression, we multiply both the top and the bottom by the 2s plus 1 term. That will clear this out. So having done that here, I get the 16 times the 2s plus 1. And then this is now also multiplied by 2s plus 1. So we have that. And then this leaves just 1 here. And then to simplify that, we'll just rewrite the numerator and the denominator. We can multiply that out. So 8s times 2s is 16s squared. And then the cross terms are going to give us 2s here, and then an 8s for the outer terms. Your FOIL, I guess, if you remember it like that. So that'll be 10s total. And then we have 1 times 1, which is 1, of course, plus another 1 gives us the 2 here. Okay, then we're going to want to rationalize this. Now, of course, you have a common factor of 2 we could factor out, but more to the point, we really want to make this coefficient in the denominator here be 1 for the s squared. That makes it a little bit easier to do. So I'm just going to divide the top and the bottom by 16. So that leaves 2s plus 1. And then the denominator, I have to, of course, divide everything by 16. So this becomes s squared. And 10 over 16, that's the same as 5/8, or 0.625. And 2 divided by 16 is, of course, the same as 1/8, or 0.125 in decimal notation. Now, in Circuit Tutor, you can enter these as fractions if you like, or you can enter them as decimals. If you do enter as fractions, it'll just get converted right away to decimals. Now, we can't enter it in this form, however, because we need to first factor it, as it already pointed out to us. So to factor it, we use the quadratic formula, obviously, to factor a quadratic. And so if ax squared plus bx plus c equals 0, the standard quadratic formula that hopefully you have memorized is negative b over 2a plus or minus the square root of the b over 2a, the same thing squared, minus c over a. That's, again, the improved formula where it's easier to compute than the one that they probably teach you in high school. So here, the negative b is just going to be our negative 0.625 divided by the 2. The a is 1 here throughout, and that's one of the reasons I normalized that. And then we have plus or minus the square root of that same thing squared, minus the c over a, which in this case is just the c value of 0.125. And then we can evaluate that. And we do notice that this is going to be less than 0.125 when we divide that and square it. So it's going to be an imaginary value here. So putting that into our calculator then, they can handle complex numbers. We get negative 0.3125 plus or minus j, which is the square root of minus 1, of course, times 0.1654. And then the units are going to be inverse seconds, because that's always the units of complex frequency. That's why we call it a frequency, is because it's basically per second. Okay, and having found those values, then we're going to insert that here to factor this. So we'll write 2s plus 1 in the numerator. And then here, remember that we have to take s plus this value, because otherwise this wouldn't be a root. It wouldn't equal 0 when we plug this in. And then we have to have minus, for the upper sign, we have minus this value now, changing both signs. And then for the second term with the lower sign, that becomes s plus the 0.3125 plus the j times the 0.1654. Again, changing the sign from minus to plus now. And we check that the s times s is indeed s squared, which is what we had here. Now, if you had not factored out that 16, then you would have to insert a constant of 16 in the denominator, because the s squared is never going to equal something other than 1. That's one of the reasons I like to just make it 1 in the first place. But otherwise, you'd have to put the constant in there, and that would have canceled out the 16. So, of course, the result would have been the same. But I personally prefer this way of doing it. Okay, now we're going to have to do partial fractions, but we're not ready for that yet. So let's go ahead and just enter this form into Circuit Tutor so it can check that to make sure we don't bother doing partial fractions on something that isn't correct. So we'll use parentheses to enclose the numerator of 2s plus 1. Have to always put that in parentheses, or you could use square brackets, either one. And then in the denominator, I'm going to have a product of two terms, so I do need to use a square bracket to enclose the two terms, which will each then go in parentheses. I'm not allowed to use parentheses around parentheses in this particular program. So we're going to go s plus 0.3125 minus a j 0.1654, close parenthesis. And then we have to put the second term, so it's s plus, again, the 0.3125 minus j is 0.1654. And then we close parentheses there, and then we have to close the square brackets to make sure everything matches. And let's see. Oh, I made a typo there. That was actually supposed to be the plus sign on the second term, right? That's why it's complaining that I've got two factors of the same type. So that's a good warning. Okay, so that's correct, and it's always good to proofread so you don't waste attempts here. So we've got that correct now with the plus sign. So now we'll check that. And that is correct. Okay. So that's been printed for us, and it reminds us the next step is going to be to do the partial fraction expansion of this so that we can go back to find v naught of t in the time domain. Okay, so it's put us into that mode, and then we select the only option, the partial fraction expansion, and we're going to do v naught of s, of course, so we put that as our sought variable, equals, and then we have to decide the number of terms. Well, there's two poles here, a complex conjugate pair, so we need, therefore, two terms for the expansion. And since it's a voltage, those are both going to be volts, so I'll put that in as volts now in both cases. And let me also point out that because we did get complex conjugate poles here, that means that our circuit is going to be underdamped. That means it will exhibit exponentially damped oscillations. So that's something just to anticipate based on the math that we've already done. Okay, so now I've done the partial fractions here on paper. So we basically started with this expression, and we set that equal to a over this term plus what will have to be a conjugate or a star over this, which is, since this is the complex conjugate of this, they have to be complex conjugates to add up to the original real value. Okay, so now to find a, we can simply use the heaviside or method of residues, or the heaviside method, and multiply through by the denominator here, which is the s plus 0.3125 minus j 0.1654. And then we set s equal to minus 0.3125 plus j 0.1654, which will basically end up multiplying this by 0, so that term goes away, and we're left with nothing but a on the right-hand side. On the left-hand side, this first term will cancel out, and then all we have to do is set s equal to that value I just quoted down here in both of the two remaining terms. So in the numerator, we have s times that minus 0.3125 plus j, etc., and then that's plus the 1 here. And then in the denominator, we only have this term, so we put in that same value of s that's here, right here, and then we add the constants, which are the plus 0.3125 and the plus j times that value now. Then we can notice that it will simplify. We don't necessarily have to put everything into the calculator. We can just cross that out as a minus and a plus. And now we can enter all of this expression into our calculator that does complex numbers, like a TI-83 or 84, for example. And when we do that, that will evaluate right away. And by the way, if you need help on using the calculator, there is a separate video on doing that. And also many of the AC circuit analysis problems show a lot of details of actually examples using that calculator. So anyway, here we're going to get 1 minus j 1.134. And in terms of, that's in the rectangular form, and I can also put it in polar form, which the calculator will also readily provide by pushing a button. So we get 1.512 angle minus 48.59 degrees. And I'm going to need that when I find the basically the magnitude and the phase for the inverse transform. And the rectangular form is going to be needed to put it into Circuit Tutor here to check the partial fraction expansion. So I'm going to enter a here in rectangular form, which is the only form accepted here. So that's 1 minus j 1.134. And then in the denominator, that's going to be that s plus 0.3125 minus j 0.1654. And then here we have to take the complex conjugate of that, so it's going to be, actually I'll just copy everything over, it'll probably be quicker. And I'll copy all this too. Control C, Control V. And then I'll change this to a plus sign here to make the complex conjugate of that. And then do the same thing down here with the plus sign, replacing the minus sign. Okay. And so we've entered all of that, and we can go ahead and check that equation. So that is correct, and it's been printed on the screen for us down here. And we're done basically entering partial fraction expansions. We only had one sought variable, so we check no more equations. And it tells us that the next step is to do the inverse Laplace transform to get back to the time domain. And also provides a table if necessary to do that. In fact, we might want to remind ourselves of the appropriate form here, so we'll click on that. And that form can be found all the way at the bottom of this table. So you see this form here basically is similar to what we have over here, except this is written in polar form, whereas we've written in rectangular. That's why I also wrote the polar form over here for ready use. And when we have the sum of those two things, that's going to give us a single exponentially damped cosine term. Now, in math class, you may have learned to do things in terms of cosine and sine, but then that would make it difficult to sketch as well as difficult to understand phase relationships. So that's why we like to use this combined term with a single cosine function with a phase angle that can represent any sinusoid and then have the exponential damping. So the prefactor here will be twice the magnitude here, and that magnitude was 1.512, so I've already computed that as 3.024. And then remember that the alpha in the denominator, which is the 0.3125 here, that's identified there, and the beta is going to be the coefficient of j, the positive value there, so it's 0.1654 radians per second. This is inverse seconds, or neppers per second, if you like. And I should have also pointed out, very importantly, that in identifying these two terms, remember it's always the s plus alpha minus j beta that we identify as the main term here, the a that I've called it. This other one that we identify as the a conjugate, that has to be over the alpha plus j beta term, s plus alpha plus j beta. If we mix those two up, we'd have the wrong phase angle in the final result. It would be negative of the correct value. So we need to make sure that we identify this with our a k basically, and not with the k conjugate that's written over here. Remember, when you change theta to minus theta, that's like taking the complex conjugate, because remember that angle symbol just really means e to the j theta, and this means e to the minus j theta. That's just a shorthand to use the angle symbol. Okay, so now we'll select the inverse transform, so we can enter that, and it's going to remind us that there's an extra set of palettes, or an extra palette of terms rather, if we needed those. We won't need them here because this is just a pure cosine and a pure power law, which we don't need in this particular problem, but you might need sometimes. Okay, so we have our v naught of t equals, and we're going to really have just a single expression here, or single term, so I don't really need brackets in this case. And it's going to remind me that the coefficient of the cosine should always be positive so that we don't get confused about the phase angle. Otherwise, it might mark it wrong if you don't do that. Okay, and so our coefficient there is going to be the 2a, that's the 3.024. And then we always have a decaying exponential, not a rising exponential, because if it was rising, that would blow up, and this would be an unstable circuit that would literally blow up too. So that's usually not too good. And this is written as e to the negative t over tau rather than as the e to the minus alpha t, as we assumed in that table. So we have to take the reciprocal then to get the tau. The reciprocal of the alpha, I've already computed, the reciprocal of 0.3125 is just 3.2 seconds. So I put that in here. And then again, this is going to be the beta value as the angular time frequency here. So that's the value of the 0.1654, rather low frequency, but that's just an artifact of our values. And then the phase angle is minus 48.59, or you could probably call it just 48.6 would be fine. And then we also need the u of t term, so I'll put that in, and that includes the units. Now remember, we have to have that u of t term or it will not accept the answer, so don't forget to put that. Here it doesn't need to be outside brackets because we just have one term. Okay, so now we can check that. And that is correct. And now we just say no more equations. And it'll always give us the PDF transcript of our work, including any incorrect steps. And you can use that when you're studying. Just use the review work button on the level menu to get that. And we can also, if there's any doubt about what we did, we can look at a full explanation of the complete solution here, which I'm just going to display for sake of completeness. But that will take a minute to compute and plot everything. Okay, so there's our original circuit in the time domain, and it's showing the conversion from time domain to the Laplace domain. And then as we scroll down here, we see also where we combine those two impedances in parallel. Shows the calculation for that in a couple of different ways. And then it gives us the detailed explanation of how we did this and found the voltage divider formula. And then shows, of course, all the details of the inverse transformation. And so all that can be used if you had any questions about how to work the problem. And then the review work button would have been here. So that concludes this example.